Hello everyone, welcome to Civil Galaxy. I am Dr. Pruthviraj B S. Today we shall discuss a module from the subject structural analysis, that is consistent deformation method. If we look into the classification of structures, we are having two types of structures. First one is determinate and second one is indeterminate structure. To make it simple, in any structure, if the number of reactions are less than or equal to the available equilibrium equations, then such type of structures are called as determinate structure. For example, if I consider a beam AB having a hinge support at point A and having a roller support about point B, if I see the reactions for this particular beam, I am having one vertical reaction about point A where I will call it as RAV. Also I am having one horizontal reaction about point A denoted by RAH. Similarly, at support B, I am having only one vertical reaction at point B since it is a roller support. So now the number of reactions are 3 and the available equilibrium equations are also 3, that is sigma Fx is equal to 0, sigma Fy is equal to 0 and sigma M is equal to 0. So since my R is equal to E here, such kind of structures are called as determinate structures. Similarly, in any structure, if the number of reactions are greater than the number of available equilibrium equations, then such kind of structures are called as indeterminate structure. For example, if I consider a fixed beam, fixed at both the ends, this is A and this is point B. Now, if I want to write the reactions for this beam, I am having one vertical reaction about point A. Similarly, I am having one horizontal reaction about point A and I am having one moment about point A. Similarly, about point B, I am having one moment about point B and one vertical reaction about point B and one horizontal reaction about point B. Since the total number of reactions are 6 and the number of available equilibrium equations are 3, here R is greater than E, that is 6. The total number of reactions are greater than the number of available equilibrium equations. This type of structure is called as indeterminate structures. So, this consistent deformation method is used for analyzing indeterminate structures. To note few key points of consistent deformation method, we shall see some of the key points for consistent deformation method. So this consistent deformation method is based on compatibility. First point. Consistent deformation method is based on compatibility. Second, since this method was first introduced by two persons, namely Maxwell and Moore. Hence, this method can also be called as Maxwell-Moore method. Third point to remember here is consistent deformation method was the very first method which was used for analyzing or for analysis of statically indeterminate structures. Statically indeterminate structures. Analysis in structural engineering means to find out the unknown parameters such as reactions, shear force, bending moment, displacements, and rotations. And the fourth point to remember here is this consistent deformation method is a force method. There are two types of method, force method and displacement method. So consistent deformation method is a force method where in this method the redundant forces are considered as the primary unknowns. So in force method, redundant forces are considered as the primary unknowns. To understand this in a better way, let us take an example of a propped cantilever beam. This is point A, this is point B. Now, if you want to write the reaction for this propped cantilever beam, we are having a vertical reaction about point A and we are having one horizontal reaction about point A, and also we are having one moment about point A. Since the prop support is a roller support, here we are having only a vertical reaction about point B. So now the total number of reactions are 4 and the number of equilibrium equations are only 3. So now if I want to find out the static indeterminacy of this particular propped cantilever beam, that is ds, we'll get 4 minus 3 is equal to 1. That is, this 1 is called as the extra force or the redundant force. That means out of these 4 forces, we have to consider one force as an redundant force so that this indeterminate beam can be treated as a determinate structure. So to illustrate this one with example, we will take two separate cases. We will consider two separate cases. That is, this same propped cantilever beam where I am having one redundant force, one extra redundant force. If I take if I consider two cases, that is case 1, I can consider the reaction about point B in the vertical direction as the redundant force. If I consider this force as the redundant force, then the same propped cantilever beam can be treated as a cantilever beam alone. That is, this is point B where I have treated this force as redundant force. Now I am remaining with only 3 forces, that is reaction about point A in the vertical direction and reaction about point A in the horizontal direction and a moment about point A. This is the first case. Second case, if I consider, if I consider this moment about point A as my redundant force, then the same proper cantilever beam can be treated as a simply supported beam, where point A will be treated as a hinge support and point B will be a roller support. That is, now this is point A, this is point B. So now this point at point A, we are having a vertical reaction about point A and we are having one horizontal reaction about point H and we are having one vertical reaction about point B. That means we have taken, out of these four forces, we have taken one force as the redundant force, and we have considered two cases here, and we have converted the statically indeterminate structure into a determinate structure. So now R is equal to 3 and E also is equal to 3 here. It becomes a determinate structure. Similarly here, my total number of reactions are 3 and the number of available equilibrium equations are also 3. So next we shall see the procedure. So next we shall see the procedure which is involved for analyzing a indeterminate beam by using consistent deformation method. We shall see the procedure. So while analyzing a beam by using consistent deformation method, my first step is to find out degree of static indeterminacy, to find out ds. Second, after finding out the degree of static indeterminacy, I should choose the redundant force. I should choose the redundant force. I should choose the redundant force and then convert or make indeterminate beam indeterminate structure to determinate. Third point, I can take it as to find out the deflection, to find deflection due to external loading, to find deflection due to external loading, and the fourth point I can consider here is removing the external load, and to find deflection due to redundant force. And the fifth point I can consider here is comparing the point number 3 and point number 4 by applying the compatibility equations. By applying compatibility equations. So before going into the numericals, we shall see the standard deflection equation for different cases. For that, let us consider 3 column serial number, and I will call it as cases, and then we shall take here the deflection for that particular case. So if I take the first case where I am having a cantilever beam subjected to, this is point A cantilever beam subjected to a point load at the free end, carrying a load of W kilonewton. So for, and having a length of L, this is point B. So for a cantilever beam which is loaded with a point load at the free end, the deflection will be delta is equal to WL cube by 3EI. Similarly, if I consider the second case where I am having a cantilever beam, this is A, this is B, a cantilever beam of total length L meters having or subjected to a UDL over the entire span of W kilonewton per meter. So for this one, the displacement will be delta is equal to W L to the power of 4 by 8 EI. Similarly, if I consider the third case, if I am having a cantilever beam subjected to a point load at the midspan having an intensity of W kilonewton. So consider this as A, this as B. So for this particular beam, the deflection will be W A cube by 3EI. Similarly, if I consider the fourth case, a simply supported beam having a total length of L meters subjected to a point load at the midspan having an intensity of W kilonewton. So for this, the displacement will be W L cube by 48 EI. Similarly, for the fifth case, if a simply supported beam carrying a UDL over its entire span having an intensity of W kilonewton per meter and the length is L, this is A, this is B. So for this particular beam, the deflection will be equal to 5 WL to the power of 4 by 384 EI. So these are the standard deflection equation where we have to remember for our future numericals, so that it will be easy for analyzing. So now let us take a simple problem, a simple numerical, and see how we can solve or analyze that particular structure by using consistent deformation method. So for that I will take a simple numerical. We shall consider one propped cantilever beam subjected to an UDL of intensity W kilonewton per meter. This is A, this is B, and the total length is L meters. So we have to analyze this proper cantilever beam with the help of consistent deformation method. So as we know the procedure, my first step will be to find out the degree of static indeterminacy, to find ds. If I want to find out the degree of static indeterminacy, first I should know the number of reactions and the number of available equilibrium equations. So here I am having one vertical reaction about point A, and I am having one horizontal reaction about point A, and also one moment about point A, and about point B, which is having a roller support, I am having one vertical reaction about point B here. So the total number of reactions are 4 and the available equilibrium equations are 3. So now if I want to find out my ds, that is degree of static indeterminacy, which will come to 4 minus 3, which is 1. That means I am having one extra force, or one force needs to be treated as an redundant force here. So step 2, as we know, we have to treat out of these 4 forces, we have to treat only one force as a redundant force, so that this indeterminate structure will be converted into a determinate structure. So here I will treat reaction about point B, this RBV, as the redundant force or redundant reaction. So now if I consider this reaction about point B in the vertical direction as the redundant force, the proper cantilever beam can be treated as a cantilever beam, which is a proper cantilever beam will be treated as a cantilever beam. So here this is point A, this is point B, having a load intensity of W kilonewton per meter, having a total length of L meters. So now I need to find out the deflection for this cantilever beam, which is subjected to an UDL. The deflection will be in this fashion. That means I need to find out the deflection about point B here. So we know from the standard deflection equation formula, whenever a cantilever beam is subjected to a UDL, the deflection will be equal to WL to the power of 4 by 8 EI. This I will call it as my equation number 1. Next, third step, after finding out the deflection, I have to remove the external force. Then I have to apply the redundant force. Removing the external force and applying the redundant force about point B. This is B, this is A. Now I have to find out the deflection due to this redundant reaction, which will be in this direction. So now I need to find out the deflection due to the redundant reaction, where I will call this as Y about point B. This was deflection about point B due to external loading. Here YB, deflection at point B due to redundant reaction. Now from the standard deflection equation, I know that whenever a cantilever beam is subjected to a point load at the free end, I am having a deflection of WL cube by 3EI. Since my W can be represented by RBV, I will take it as reaction about point B in the vertical direction into L cube by 3EI. So now I need to apply my last step, that is applying the compatibility conditions. So this equation I can call it as equation number 2. So now if I compare the equation number 1 and equation number 2, comparing equation 1 and equation 2, I will have WL to the power of 4 by 8 EI, which will be equal to RBV L cube by 3 EI. So now if I cancel EI and L4 and L cube, I will be remaining with reaction about point B in the vertical direction, which will be equal to 3 W into L by 8, which is in the upward direction. So out of this 4 reactions, I have got one reaction, that is vertical reaction about point B, which is in the upward direction. So now I need to find out other 3 reactions, that is reaction about A in the vertical direction and reaction about A in horizontal direction and moment about A. So now to find out reaction about A in the vertical direction, I can take sum of all the forces moving in the upward direction, that is RAV plus this force here, that is RBV minus the total load coming in the downward direction. Since it is a UDL, it will be minus W into L, which will be equal to 0. So as I know RAV, we need to find out, where RBV value we are having, that is plus 3 WL by 8 minus WL equal to 0. So now if I want to find out my reaction about point A in the vertical direction, I am having WL minus 3WL by 8. 3WL by 8. Sorry, we'll continue here this side. So RAV will be equal to WL minus 3WL by 8. So if I substitute this one, I will get, if I take 8 as my LCM, I am going to get so here I am going to get 8 WL minus 3 WL, which will be equal to 5 WL by 8. That is nothing but my reaction about A in the vertical direction, which is also in the upward direction. So now out of 4 reactions, I have got 2 reactions, that is vertical reaction about point B and vertical reaction about point A. Remaining is horizontal reaction about point A. Since there is no horizontal reaction about point A, it will be 0. So the last reaction or the last parameter I need to find out is moment about point A, where moment about point A, I will take it as, where I know moment is nothing but force multiplied by perpendicular distance. I can take, instead of taking moment about A directly, we shall take sigma moment, we shall take sigma m is equal to 0, we shall take sigma m is equal to 0, where I will be having about this point moment A. So force multiplied by perpendicular distance, it will be in the anti-clockwise direction, minus RBV into perpendicular distance L meters plus W into L load into distance into half the CG, which is a UDL, minus moment about A, since it is rotating anti-clockwise, will be equal to 0. So now I will be having moment about A equal to RBV into L minus WL square by 2. If I substitute RBV value, which is nothing but 3 WL by 8 into L minus WL square by 2. I can simplify this by writing 3 WL square by 8 minus WL square by 2. So now if I further simplify by taking LCM 8 here, which will be nothing but 3 WL square minus 4 WL square comes out to be minus WL square by 8, which is nothing but my moment about point A, which is rotating in the anti-clockwise direction. So now to summarize this entire problem, I have got four unknowns. I'll write here only. I have got four unknowns, which is nothing but reaction about point A in the vertical direction and reaction about point B in the vertical direction, reaction about point A in the horizontal direction, and moment about point A. So now reaction about point A in the vertical direction, I have got 5 WL by 8, which is acting in the upward direction. Similarly, reaction about point B in the vertical direction, I have got that is 3 WL by 8, which is also acting in the upward direction. Since there is no horizontal force here, my reaction about point A in horizontal direction is directly taken as 0, and the moment about point A, I have got that is minus WL square by 8, which is in a anti-clockwise direction. So this is the procedure to find out the unknown reactions for an indeterminate structure using consistent deformation method. So similarly, we shall see another example or another numerical in the next coming classes. Thank you.